Your own, Carson. Name. Oh, we have good old Ann. A circular loop. So as soon as I see the word loop, first of all, Keaton, what are they asking me to find? The average what? So EMF is this. I have two main equations. I have this one and I have this one. This is the one I use when there is a loop or a coil. Now, you can use this one for everything. You can figure out a way to kind of come up with a changing flux, but I don't advise using that one for everything. If you take physics in university, you'll learn something called Maxwell's equations, where, Carson, we take this and we turn it into its calculus notation. And in fact, there's four equations, Maxwell's equations. There's four of them. They describe everything with light and magnetism and electricity. They're wonderful. But here, I'm going to be using, we call this one Faraday's law. So let me erase all this. It's going to be negative n change in flux over time. Liam, can you read me the very first word? It's a single letter. Number one, the very first word, it's a single letter. How many loops are there? So n is 1. Yay. If not, there might be more loops, but don't miss that little notation. It says it has a diameter. We don't use diameters in physics. We use radiuses or radii. So I'm going to make a little note. R equals 0.05 meters. And now I'm good to go. I know that n equals 1. I know that the change in time equals 0.2. What we're going to spend most of our time finding is the change in flux. So the change in flux, and until you get good at this, Jacob, I would advise don't take shortcuts. I'm going to say, well, change in anything is final minus initial. Now, the fact that we're removed from the magnetic field, Raghib, if I'm removed from the magnetic field, what's my final flux as a number exactly? So I can do that. Okay. How do I find flux? Flux is magnetic field times area. So it's going to be, the minus sign drops down like a domino. The magnetic field times the area. What's the area? Well, it's a circle, so it's going to be the magnetic field with the negative in front of it times pi r squared. And I think I told you, I did give you the area of a circle on your formula sheet, I believe. Yes? So the change in flux is going to be negative b 0.5 times pi times 0.05. Don't forget the squared. Yep, wrong button, Mr. Dueck. Let's see. Negative 0.5 times pi times 0.05. Don't 0.05. Don't forget the squared. I get a change in flux of that. I'm going to write negative 0.0039, but I'm going to use my answer button. Negative 0.0039. Ooh, what were the units for flux? It was our final brand new unit of the year. Webers. Walk it over to here. I'm going to get the EMF equals negative 1, negative 0.0039, but I'm using my answer button, divided by 0.2. What's the average voltage we'll get? Why is it the average voltage? Because it will be changing as the coil left the magnetic field from maximum to zero is the flux. So it wouldn't be a constant voltage. We're going to get an average. It's going to be negative. Do I need to actually type the 1 on my calculator? No. So it's going to be negative times, you know what? I'm going to go like this. Negative 1 times negative, just so I can see there's a minus minus, which is a plus. Answer button. Oh, no, hang on. I already got the negative answer there. I'm good. Negative answer button divided by 0.2. And I get 0.0196 volts. Is that correct? I see Raghib saying yes. Yes. Okay. 0.0196 volts. Is that a big voltage, Achi? Or no? How could you get more? Well, it's a single loop of wire. Put 1,000 loops of wire in there times 1,000. Yeah, now I'm getting 20 volts. Now that's better. Okay, so or change the time or change the magnetic field. If you got this right, I would give you 4 out of 4. Otherwise, 1, 2, 3, 4, 5, 6. Yeah, I'd probably go something like this. I would give you a half mark if I saw that. I would give you a half mark if I saw that. A half mark for that. A half mark for the numbers. A half mark for finding the flux. A half mark for that, and then 1 whole mark for the answer. Probably something like that. Number 2, a wire moves perpendicularly through a magnetic field. Okay, now we're talking about a wire. They want the induced EMF. Now I'm going to use the EMF equation for a wire, which is BLV. And they all have to be perpendicular to each other. Hey, it did include the word perpendicular. This is good. So it's going to be the magnetic field, 0.4, pretty big magnetic field, L, 0.5, V, 25. This is straight plug and chug. As far as I'm concerned, Ragav, how many variables are there in this equation? How many variables are there in this equation? Try again. 4. If I give you any 3, you can find the fourth. So I'm going to say you can get the B by itself, or the L by itself, or the V by itself, yes? In this case here, it's going to be 0.4 times 0.5 times 25, and I get 5.0 volts. 2 marks, I would give you 1 mark for the equation, half mark for the numbers, and a half mark for the answer. Oh, now they want the current. Well, let's see. Current is V over R. Although, Carson, since I'm finding an induced voltage, I'll use the EMF symbol, but if you put a V there, that's fine. It's going to be 5 divided by 6. I should be able to do that in my head. Is it 0.86 repeating? 0.83 repeating. Sorry, you're right. 0.833 amps. 1 mark for that, half mark for the numbers, half mark for the answer. So you're going to notice V equals I times R, Evan, and you probably noticed in the homework, very much fair game in this unit as well. Well, of course, we're generating a voltage. Current and resistance are now back in play if we want to try and actually make this part of a circuit. I like number 3. I like number 3. It's around the quiz. Why? Oh, okay. The key to realize here, we have a coil of wires. Oh, N is 750. They gave me the area. The key to realize here, Justin, is the magnetic field has changed direction. You need to let one way be positive, one way be negative. Now, there's no firm rule for which one's positive or which one's negative. So for my final answer, I will take a positive or a negative answer. I chose to let this one be positive. I chose to let this one be negative, but you could have done it the other way around. They want the average induced EMF in the coil. That's going to be Faraday's law. I said, okay, N is 750, the time is 0.25, I need to find the change in flux. The change in flux is going to be final minus initial. The change in flux is going to be BA final minus BA initial. What's changing here? The area? No, this time the magnetic field is changing. So the change in flux, final magnetic field, I said was 0.45. And the area was also 0.45, strangely enough. Minus initial magnetic field, I said was positive 0.75. And the area was 0.45. You could have the final be positive and the initial be negative. It's perfectly acceptable. I did it this way, and so when I did that, I got a change in flux of negative 0.45 times 0.45 minus 0.75 times 0.45. I got a change in flux of negative 0.54. I would also accept Webers, positive 0.54. It's all relative. So I walked this over to here, and I said, okay, now I can calculate this. Negative 750 times negative 0.54, all divided by, was t 0.25, I think? Yeah. What's the average induced EMF? Let's see. Negative 750 times negative 0.54 divided by 0.25, 1,620. I would have to take either positive or negative 1,620 because you might have let the first one be negative and the second one be positive. It's all relative. Which, by the way, you're getting an alternating current here, so you are going to get a positive and a negative voltage anyways. Ooh, what's the average current? Same old. Oh, for full marks, what was this? 5 marks, Mr. Dueck? I would probably go 1 mark for that. Hang on, Mr. Dueck. Let's do some part marks, Mr. Dueck. I can go a half mark for that. I would go a half mark for that. I would go a half mark for that. I would go a half mark for that. You know what? I'd probably go 1 whole mark for finding that, but it could be positive or negative. So I'm going to go 1 mark for that. I'm going to go a half mark for that. I need more marks, Mr. Dueck. I'm going to go 1 mark for that. You know what? 1, 2. Good gosh. Give you 1 whole mark for that. What am I up to? 1, 2, 3, 4.5. So what am I going to do, Mr. Dueck? I'd probably, oh, you know what? I'll give you a half mark for those numbers there. How about that? But again, if you got the right answer, I'd give you 5 out of 5. Average current, same old, same old. Current is V over R. But I'll, again, Kevin used my EMF symbol. So it's going to be 1,620 all over 100, which I'm pretty sure is, what, 16.2? 1.62. Oh, boy, Mr. Dueck. It's for 16.2, right? 16.2, yeah? 16.2 amps. Mr. Dueck, what if I said it was negative? I guess I would accept that, but typically for currents, we write them as positive. The direction comes from show me the circuit, and I'll show you which way is downhill. Last one. A single rectangular loop of wire is being pulled out of a magnetic field at a constant speed. Now, this is a loop, which means you can solve this with Faraday's law, but I want you to notice that this arm and this arm are moving parallel to the velocity, so you're not going to induce in voltage in those sections, and this section is not in the magnetic field. So even though this is a coil of wires, I'm going to use BLV. I'm going to use this is the section where the wire is being induced, where the current, sorry, where the voltage is being induced. First of all, they want me to find the speed of the loop. I think I'm going to say, okay, that's a hint. I want to use the one with the speed in it. Raghav, how many variables are there in that equation? Psst, how many variables are there in that equation? As I said earlier, if I give you any 3, you can find the 4th. So I think it's going to be the voltage divided by BL. What's the voltage? What's the EMF? Oh, 0.75 volts. Now, the other thing that I could have done is I could have given you the current, and since you know the resistance, you could figure out the voltage. That's another little sneaky move I can do. But I gave you the voltage. It's 0.75. I'm sure I gave you the magnetic field in Tesla's 0.25. And the length was 0.42 meters. 0.75 divided by bracket 0.25 times 0.42, and I get the speed must be 7.14 meters per second. Is that correct, folks? People nodding? If you got that right, 3 out of 3. Otherwise, I would probably go half mark if I saw that, 1 whole mark for that, half mark for the numbers, and 1 mark for the answer. What's the current through the resistor? Okay, same old, same old. Current is going to be that. It's going to be 0.75 divided by 0.5. Is that 1.5 amps? Okay. What else could I ask? Evan, I could also ask, what's the magnetic force on this coil? Because, well, first of all, let's answer part C. Well, first of all, Mr. Dueck, put your marking scheme in. I would go 1 mark for that, half mark for that, half mark for the answer. Which way is the current flow? So here's my token proton. I don't care about the other arms because 2 of them are parallel and 1 of them's not in the magnetic field. Which way is this moving? To the right. So I'm going to point my right thumb to the right. Magnetic field into the page. You know what? This proton is going to feel a force this way. It's going to feel a force that way. It's going to move this way. It's definitely going from B to A in this case. But another good follow-up question, hint, hint, would be to now say as a part D, what's the magnetic force, magnitude, and direction? So now that this proton is moving up, if I point my thumb up the page, magnetic field into the page, which way is the force? Which way is your palm pointing, Kevin? To the... You'd feel, as you tried to pull this out, if you were the one pulling this coil out of the magnetic field, you'd feel a force opposing you. Of course you would. That's Lenz's law kicking in. Whatever you try and do, nature says, no, you don't. And so I could calculate the force. It would be Bil, B-I-L. That's all fair game from last unit still as well. Can you give yourself a clear score on this quiz out of 21, please? Any lawyering with me? Now is the time.